You've been here before. That moment when you type your password, confident, and the screen shakes. Wrong. You try again. Different capitalization maybe. Added a number at the end. Wrong again. And then the button nobody wants to press. Forgot password. Here's what most people assume happens next. The website looks up your password in its giant list of users. It finds your email, sees your password, and sends it to you in an email. You log back in. Simple. But here's the thing. The website cannot send you your password. Not because it's too complicated, not because of privacy rules, because it genuinely does not know what your password is. It never did. So if the website doesn't have your password, what exactly did it save when you first signed up? That's the question. And the answer changes how you think about every account you've ever created. To understand it, we have to look at the math of secrets. Let's go back to the day you created your account. You chose a password, typed it in, hit submit. In the half second between you pressing enter and the website saying account created, something happened to your password. Something permanent. The website took your string of characters and fed it into a one-way mathematical machine. Your password was fed into something called a hash function. Think of a hash function as a blender. You put a word in, you get a completely different string of characters out. My password 123 goes in. Something like 7F4A82C9E1D comes out. But this isn't just a random shuffle. It's a deterministic mathematical operation. If you put the same word in 1,000 times, you get the exact same string out every single time. The magic of a hash function is that it's one way. In math, some problems are easy to solve forward, but nearly impossible to reverse. Think of it like a giant multiplication problem. It's easy to multiply two prime numbers together. But if I give you the result and ask which two prime numbers I used, that's a nightmare. A hash function uses modular arithmetic and bit shifting to ensure that you can turn a password into a hash, but you can never turn a hash back into a password. And here's why that matters. If someone breaks into the website's database, if a hacker steals everything, they don't get your password. They get 7F48B29E1D, which tells them nothing. This is why, when a website gets hacked, companies tell you to change your password out of caution. They're not being dramatic, they're being honest. Your hash was stolen. Your actual password, technically, wasn't. But wait, if I know the website uses a specific blender, let's call it SHA-256, couldn't I just take every common password in the world, run them through that blender myself, and see if any of the outputs match the one I stole? This is the fundamental loophole in basic hashing, and hackers have been exploiting it for decades using something called a rainbow table. A rainbow table is a cheat sheet. It's a giant list of every common password, like 123456 or password or I love you, already pre-blended into their strings. These tables aren't small. We're talking about petabytes of data containing billions of combinations. If a hacker steals 1,000,000 hashes, they don't have to reverse the math. They just have to look for matches on their cheat sheet. It's fast, it's efficient, and it's how billions of accounts are stolen every year. So how do we break the cheat sheet? How do we make it so that even if two people have the exact same password, their blended string looks completely different? How do we make it so the hacker has to start from scratch for every single user? We add a secret ingredient, something called a salt. A salt is a long, unique, random string of characters that the website generates just for you the moment you sign up. It's not secret. It's stored right next to your hash in the database. But when you type your password, the website adds your unique salt to the end of it and then puts it in the blender. My password 123 plus Z7K9X2 equals a completely unique hash. Now, even if 10,000 people use the password 123, every single one of them has a different salt, which means every single one of them has a different hash in the database. The hacker's cheat sheet, the rainbow table, is now useless. They can't pre-compute the hashes anymore because they don't know what the salt will be for each individual person. They would have to build a new cheat sheet for every single user on the site, and that would take until the end of the universe. But is salting enough? The year is now 2026, and your laptop is 1 billion times faster than the computers that first invented hashing. If a modern computer can try 10 billion hashes per second, does it even matter if the cheat sheet is gone? If they can try every possible 8-character password in a few hours, your salt is just a speed bump. This is the hardware race. Hackers aren't using normal computers anymore. They're using clusters of graphics cards, GPUs. While your CPU is like a single genius who can solve one complex problem at a time, a GPU is like 10,000 students who can each solve a simple problem simultaneously. Hashing is a simple problem. A single high-end GPU can run millions of SHA-256 hashes a second. Put 100 of them in a rack, and you have a machine that can guess its way through almost any common password in minutes. How do we win a race against hardware that gets faster every single year? How do we protect a password from a machine that can try 1 billion combinations a second? We do something that sounds counterintuitive. We make the blender intentionally slow. We move from fast hashing to adaptive hashing. Modern security standards like Argon 2 or bcrypt are designed to be heavy. They don't just blend the password once, they blend it thousands of times. They require a specific amount of memory. They are designed to take exactly half a second to complete on a modern server. This is called key stretching. For you, half a second is nothing. You type your password, hit enter, and half a second later, you're logged in. But for a hacker trying to guess 10 billion passwords, that half-second delay is a nightmare. It turns a 4-hour attack into a 150-year project. Security isn't about being unbreakable. It's about making the cost of breaking you higher than the value of what's inside. We are weaponizing time against the attacker. But is there a way to peek inside the vault without ever guessing a password? Can a hacker bypass the blender entirely? They have a trick that doesn't look at your data, it looks at your clock. This is a side channel attack, specifically a timing attack. When you type your password, the server compares it to the database string. If the code is written poorly, it might check character by character. Does the first letter match? No. Stop. This takes a tiny, measurable amount of time. If the first letter match, the computer moves to the second letter, which takes slightly longer. By measuring these nanosecond differences, a hacker can feel their way through your password letter by letter, like a safecracker listening to the clicks of a dial. Modern systems are built to be blind to time. They use constant time comparison. They check every character, every time, no matter what. They intentionally take the same amount of time for a correct password as they do for a wrong one. They are intentionally inefficient to stay silent. In the world of security, silence is safety. So now we're back at the forgot password screen. You understand the salt, the hash, the computational cost, and the silence of the clock. But why the email link? Why can't they just let you type a new password right there? Because the link is the proof of possession. It's the only way to verify your identity without the password they don't have. When you hit that button, the server generates a long random string, something called a reset token, A7F92BC48D1. It's unique to you, and it has a death timer on it, usually 15 minutes. This token is a temporary key to a temporary door, and just like your password, the server doesn't store the token itself. It hashes the token and stores the hash. The actual token goes into your email inbox. If a hacker breaks into the database during those 15 minutes, they see a hash, not the token. They still can't reset your password. They need the clear text token from your private email. This is security in depth. Multiple layers of blenders protecting every step. You click the link. The server looks at the token in the URL. It hashes it. It compares it to the database. Match? Token alive? Only now does it give you the power to overwrite your old hash. The moment you submit a new password, the old hash is deleted, the token is destroyed, and the door vanishes forever. But what if everything else fails? What if your email is hacked? What if the hacker bypasses the timer? This is why the best security isn't just a better blender, it's a second door, an independent verification that doesn't rely on the same infrastructure. Two-factor authentication is the ultimate insurance policy. It says, even if you know my secret, you don't have my physical device. It uses a completely different protocol, often a time-based code or a push notification. Even if a hacker has your password and your email, they still hit a wall. 2FA is the bridge between the digital world and the physical world. Here's your ultimate safety test. A way to know instantly if a company is lying to you about their security. If you ever click Forgot Password, and the website emails you your actual clear text password, close the tab, delete your account. If they can email it to you, it means they stored it in plain text. No blender, no salt, no security. It means every employee, every intern, and every hacker who gets past their first firewall can see your password in plain sight. They are building their house without a lock on the door. Don't wait for the break-in. Leave now. This is the invisible architecture of security. You clicked one button, but behind it, a unique salt was fetched. An intentionally slow blender ran. A one-way cryptographic fingerprint was compared. A time-locked token was generated, transmitted, and destroyed. All of it to protect a piece of data the website doesn't even know. But let's be honest. Even with all this, passwords are a nightmare. The average person has over 100 accounts. Remembering 100 unique, complex strings is humanly impossible. We've reached the limit of what something you know can achieve, which is why we're entering the final act of this story, the end of the password itself. You've probably seen it already, your phone asking for your face or your fingerprint to log into a website. This isn't just a shortcut, it's a fundamental shift in how identity works. It's called a passkey, and it's designed to fix everything we've talked about today. When you use a passkey, your actual password never exists. Instead, your phone generates a private key that never leaves your device. It stays in a hyper-secure chip called a secure enclave, a piece of hardware designed to be physically impossible to read from the outside. When you log in, the website sends a challenge, and your phone uses its private key to sign it. And your face? Your fingerprint? The website never sees them. Your phone hashes your biometric data locally to unlock the secure enclave. The website only sees the digital signature. You are the key, and you are the lock. Even if the website is hacked, there is no hash to steal. There is nothing in their database that can be used to log in as you. In this future, there is no forgot password button, because there is nothing to forget. If you lose your phone, you use your backup device or a physical security key. The vault is yours and yours alone. We are moving from a world of shared secrets to a world of personal proof. The next time you see that forgot password button, don't see it as a nuisance. See it as a monument to how hard we've worked to protect the one thing we can never truly own, our digital identity. It's the result of 50 years of mathematical war. Your password was never there to recover. It was turned into a fingerprint the moment you created it. And fingerprints are designed to identify you, not to be read. The next time you forget your password, you're not locked out. You're just waiting for a temporary door that was built specifically for you. In the last 15 minutes, by math. There are 36 more moments just like this one. Things you do every day, with no idea what's actually happening underneath. Actually, every week.